Okay, liberal arts, here we are in week 2, section 2.02. We are going to be comparing data sets. And the first thing we're going to look at is box plots. Now, I really want to help you understand exactly kind of what a box plot is and how the data is represented through a box plot. Some of you might remember this from Algebra 1 or earlier. Some of you might not know what this is at all. But yeah, we'll talk you through it. We'll make sure that you understand what's going on here. All right, so what is a box plot, right? A box plot divides a list of data into 4 sections called quartiles. The plot is a data display that shows the minimum, lower quartile, median, upper quartile, and maximum of the data set. Each quartile is 25% or 1/4 of the data. A box plot can be used as part of a statistical process to analyze and interpret data. Now, I think it's a lot of mumbo jumbo. You can see what a box plot kind of looks like. Sometimes it's called a box and whisker plot because you have a box in the middle with like 2 whiskers coming off the ends of it on the left and right. But I think this really works out well when we go through kind of an example of it, right? I can help you out with that. I'm gonna stop there. Okay, so they have this nice video in 3 parts that explains the whole box plot thing and how you use your data, but I'm going to go ahead and talk you through it myself as well. So you can go with theirs, you can watch mine, whatever you find better, right? So let's list their numbers. They got 10, 6, 8, 4, 14, 11, and 3. 10, 6, 8, 4, 14, 11, and 3. Make sure that's right. Yes, okay. So the first thing we got to do is rearrange these numbers from least to greatest. So 3 is the smallest, then 4, then 6, then 8, then 10, then 11, and then 14. Okay, so from biggest or from least to greatest, from smallest to biggest, right? Now, let's start with the 3 easiest to find, in my opinion. We can find the minimum value. Minimum value, that's the lowest value. Obviously, in this case, it's 3. The maximum value, another easy one to find, the highest value, which is 14, and the regular median. Sometimes this is known as, there's a lot of names for this. You can call this the second quartile, is another term people call it. I think some people call it like something about 50 percentile or 50th percentile, something like that. Or, 50 percentile. Ooh, if I can even spell it, percentile. Right, you got that. There's lots of names, but median. You guys know how to find the median. It's just the number in the middle, right? So 1 from the left, 1 from the right, 2 from the left, 2 from the right, 3 from the left, 3 from the right. The number in the middle is 8. Now, let's say we had an even number of numbers here. Let's say we did this and we had 2 numbers left in the middle. Then we would take the average of those numbers. So if I had both 8 and 9 in the middle, the median then would be 8.5, right? It'd be the number between them, halfway between them, okay? Or the average of those 2 numbers. Obviously, we don't have that in this case. It's just 8. But what confuses a lot of people is the first quartile and the third quartile, not second. Oops. Third quartile. Also sometimes known as the 25th percentile and the 75th percentile. Well, to do those, all right, let me rewrite my number set because my eraser tool doesn't work out super nicely. Discounting the fact that we've already claimed the median, we know the median is 8. The first quartile is just the median of the first half of the set, and the third quartile is the median of the second half of the set. So if we take the median of the first half, first number, last number, right, 1 and 1, then the middle number here is 4, making our first quartile 4. And then the median of the second half of the set, obviously 10 to 14, we take those out. The median is in the middle, 11. Third quartile is 11. So that's how you find those values. Okay, now, if we draw a box plot, here's what it would look like. First, let's start with a number line. So on this number line, we'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So what I like to do is put marks on my min, max, median, all these numbers here. I like to go ahead and put a mark on there. So my minimum I know is 3. My maximum I know is 14. So you see I put a mark above 3, I put a mark above 14 as to label, my min and my max. I also have my median, which is 8. It's my median. My first quartile, which is 4. So first quartile is a mark at 4, and my third quartile is at 11. So my third quartile is at 11. So you see I've got these 5 marks. Because it's all, it's always these 5 numbers, 5 places: min, max, median, first quartile, third quartile. Now, the way a box plot works is you have a box that connects the first quartile to the third quartile. So the first quartile from 4 to the third quartile, 11, there's a box that connects the first quartile to the third quartile. And in the middle of that box, not in the middle, I shouldn't say in the middle, but somewhere inside that box is the median, right? So the median, of course, is, not in the middle of the box, but somewhere obviously in the box, because the median's going to be between the first quartile and the third quartile. Has to be. If the median is somehow not in between the first quartile and the third quartile, then you definitely did something wrong. Because remember, back in the number line, right, the median is already in the middle. First quartile, third quartile, obviously one's going to be small, one's going to be bigger, right? So median has to be somewhere inside that range. So you draw a box from the first quartile to the third quartile, and then you draw the whiskers that connect to the minimum and the maximum. So whiskers, just little lines that connect to those outer regions, outer extremities. Okay. All right, so there's your box plot. Now, something very important that a lot of people get confused by is that this box is set up in 4 quadrants. You have this gap here. You've got this gap here from the first quartile to the median. Then you've got the median to the third quartile, and then you've got the third quartile to the max, right? You've got this range, this range, this range, and this range. The thing about this is that each range contains 25% of all data values. So what that essentially means is that, let's say you just took, from the minimum to the median, right here, the minimum to the median would be 50% of all your data values, right? And obviously the last 50% here, right? 50% from the median to the max, right? So I'll explain this more as we go if this is confusing you, but it is something that's very, very important to remember, that 25% of the data is inside each quadrant, or each little section between them, okay? But like I said, I will explain that more as we go throughout this. Okay, so there you can see a box plot on a number line for that data set. I obviously showed you the one for the video that they gave you. So for concert plays, dances, and basketball football games, I'm going to choose to do just one of these. But obviously, you have 3 sets of data there. That you're going to make 3 box plots for. So let's just take one set of data. Let's not do all 3. So let's take concerts and plays. We have 125. I'm just going to list off those numbers. We have 125, 200. Oops. What's that? 200. What else we have? 360, 325. 375, 440, and 370. Okay, so the first thing, of course, we need to do is list these in order from the least to greatest. So least to greatest would be 125, 200, 325, 360, 370, 375, and then the biggest being 440. Okay, so we're going to find the minimum, maximum, median, first quartile, and third quartile. So for minimum, maximum, median, first, and third. So the minimum obviously is 125. That's the lowest number. The maximum is clearly, did I write that? It's 440, right? Maximum is 440. the median, let's take it away. So this number 1 from each side. Let's get the second one from each side, the third one from each side. Median is 360. Now the first quartile is, if I take out the fact that I've already know the median, first quartile is the median of the first group. So the median of the first group would be 200. And the third quartile is the median of the last group. So the median there would be 375. So there's our min, max, median, first quartile, and third quartile. Now, if we were to make a box plot of this, let's make a number line. And on this number line, let's go from 100. Let's go by 25s here. 120. No, going all the way to 400. Let's go by just 50. 150, 200, 250, 300, 350, 400, 450, and 500. All right, so obviously we're going to have to kind of guesstimate a little bit. So minimum 125. 125 is going to be about halfway between 100 and 150. Put a mark there. My max is 440, so 440 is going to be, kind of close to 450, but not there, so we'll mark there. Median is at 360, so 360 is going to be a little bit higher than 350, so right there. Our first quartile is at 200, and our third quartile is at 375. So this was my minimum, my maximum, my median, my first quartile, and my third quartile. Remember, the box plot connects from first quartile to third quartile. So our box connects those together. So the first quartile to the third quartile, we have a box around that. Remember, the median should be somewhere inside that box. And then we draw the whiskers that connect to the minimum and the maximum. And there's your box and whisker plot. And if we go back to the example they gave us, you can see that box and whisker plot sort of somewhat there on constants in place. Now they've already, like I said, they've done all the values for dances and basketball football games as well. They've put that all in there. They've made the box plots as well. So, but you can see, you can check your results there. You can see for constants in place, they got the 125 as their minimum, 200 as their quartile 1, median was 360, 375 as their third quartile, and max was 440. All the same numbers that we got. I'm not going to do the same thing 3 times. So dances and basketball, football games, I'm going to let you guys try to work them out and check your answers. Make the box plots as well. Okay. So remember that no matter what your box plot is, no matter what the size of your box plot is, actually, let me go back to the one that they have here and I'll screen snap it. Okay. So this is all 3 of those box plots. Now, no matter what the size is, okay, each section in the box plot is still 25%. So right here, still 25%. Right here is still 25%. Right. Oh, there's a very, very small margin, obviously, right here. This little margin there is still 25%. And then the last part here is still 25%. Okay. So everything there is still broken into 4. It's 25%. A lot of times people think that, hey, you see how this region here is very, very small? There must be very few numbers in that region. And the answer is that's false. There's not fewer numbers in that region. Okay? There's the same numbers in this region as there is in all the other ones. Okay? And again, the reason is because it's all broken into fourths and even fourths. A wider spread out area like this one is just saying that that data is more spread out. Okay? Whereas a tightly packed one like this means that the same amount of data is more tightly compacted. Okay? So if I had a list of 20 numbers, right? There'd be 5 of those numbers would fall within this range. 5 of those numbers would fall within this range. 5 more numbers would fall within that little range, and then 5 numbers there would fall in that last range. Each section would still have exactly 5 numbers in it. Okay? It's just obviously the sections are different sizes because of how spread out those 5 numbers might be. Okay? That's just an example. Obviously, that's the 5 numbers doesn't pertain to the constants in place, but I was just using that as an example, okay? So there'd be 5 numbers that would be very tightly packed in this region, which is why it's so small, whereas the 5 numbers that are packed in this region are very, very spread out, okay? So let me kind of make a secondary example here, right? Let me give you a list of some numbers. Let's say I've got 10, 11, 20, 22, 31. I want to make a list of 20 numbers here, right? And I want to put them in order just to make it work. Let's say then I've got 35, 37, 38, 39, 40. And let's say I've got 45, 62, 78, 94, 97, and then 5 more numbers at the end of this. I'm just making these numbers up just to demonstrate a point real quick. 100, 103, 105, 107, and 110. Okay, now there are 20 numbers here. I've got 5 numbers here, 5 numbers here, 5 numbers here, and 5 numbers here. My median, if I were to find the median of all this, my median would be somewhere between 40 and 45, so it'd be 42.5 right in the middle. My minimum would, of course, be 10. My maximum would, of course, be 110. My first quartile would be somewhere between 31 and 35, so halfway between that is 33. And my third quartile would be halfway between 97 and 100, which would be 98.5. Right, that's if I found those values. Right now, 42.5. Now, if I make a box plot here, my box and whisker plot would look something like this. Let's go from 0. Let's go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. Right? I'd have a minimum of 10. I'd have my median at 42.5, my maximum at 110, my first quartile at 33, my third quartile at 98.5. And then my box would go from first quartile to third quartile, and my whiskers would go there. So remember, each section had 5 numbers in it. There are 5 numbers between 10 and 33, right? And there are 5 numbers between 10 and 33. There are 5 numbers between 33 and 42.5, and there were 5 numbers between 33 and 42.5. There are 5 numbers between 42.5 and 98.5. 5 numbers, only 5 numbers, and there were, right, between 45 and 98.5. And then there were 5 numbers at the end between 98.5 and 110, and there were, right? So every section here is a different size, but they still had the exact same number of numbers in them. Every single section had 5 numbers. The spreadness of them is just how spread out the numbers were. So you see this giant gap here. Well, that's because in that space, those 5 numbers are very spread out, right? 45, 62, 78, 94, 97, very spread out numbers. Whereas this part is very tight, very small, and compacted. That's because those 5 numbers are very tightly close together, 35, 37, 38, 39, 40. So that's the space. That's how the box plot is distributed, if you will, okay? A bigger section doesn't mean more numbers. Every section has the same amount of numbers. It's just a bigger section means that those numbers are spread out further, whereas a smaller section means those numbers are more tightly closer together, right? Less spread out. That's a very important thing that a lot of students tend to forget about box plots. Shape of data, I think this is pretty self-explanatory. Symmetrical versus asymmetrical. Obviously, you can see for the bar graphs, the symmetrical bar graph is very symmetrical. The asymmetrical one has a big bar on the right side. With the box plot, you can see the box plot very symmetrical, and then a very not symmetrical box plot there on the right. Okay, because of how spread out everything is. Okay. So they have some examples here to look at. Example 1, example 2, and example 3. I believe this is for those previously listed things, yes. Yeah, we just talked about what makes a quartile so wide. Exactly. We've discussed all those things in nauseum already. So now let's talk about, well, okay, let's look at this real quick. Remember, distribution of data. If it's symmetrical, the best measure of center is the mean, basically the average. If it's asymmetrical, the best measure of center is the median, which is what we've been doing here. So just keep that in mind. Asymmetrical versus symmetrical data. Symmetrical ones would be better off with the mean, the regular average. Asymmetrical ones you'd want to use the median for. Something that a lot of quizzes like to ask a question like that. So, spread in a box plot. We've already talked about this, but we can go over it again. So how can box plots show spread in the distribution? Well, you can see the range on the graph from the minimum and maximum values. Box plots also show what is called the interquartile range, IQR. The interquartile range is that box part, right? The one that goes from the lower quartile, which is the first quartile, or the upper quartile, which is the third quartile. So lower is the same as the first quartile, and upper is the same as the third quartile. Like I said, there's lots of different names for these. Okay, but interquartile range is that box part. Okay, you made a number of observations about the data sets. For the school activities, you used mean and median to measure the center of data, and you used the interquartile range to measure the spread. Now you will explore what it means to use the standard deviation of the data set. So standard deviation is a good way to measure how spread out the data really is. If the data is not that spread out and it's very tightly compacted together, all the data points are very similar, your standard deviation will be really small because there's not a lot of spread. But if your data is really, really far spread out, then your standard deviation will be pretty large to show you that it's very spread out. The letter that we use for standard deviation is a Greek letter called sigma. Looks kind of like an O with a hat on top of it. All right, but here we're going to look at standard deviation and its spread. So the larger the standard deviation, the more spread out the data. As we mentioned, the smaller standard deviation, the closer the data points are. A standard deviation of 1 tells you that most data points are only within 1 unit from the mean. A standard deviation of 10 tells you that most of the data points are within 10 units from the mean. So again, how close to the mean they are, how not close to the mean they are, how spread out it is, right? So given the data set 14, 3, 2, 8, 6, 22, 15, 10, 16, and 18, and knowing that the standard deviation is a measure of how spread out the data are from the mean, what can you infer about data with a standard deviation of 6.31? So a standard deviation of 6.31 tells you that the most data points are within 6.31 units from the mean being 11.4. So that problem gave you the data and already found the mean for you. The mean of all that data was 11.4. But it then also tells you standard deviation. And standard deviation, again, tells you how spread out the data is. So example 2 looks back at our concert plays, dances, and games. And you could see that dances has a very spread out data set. That would mean that dances would have probably the highest standard deviation. Games, however, has a very tightly compacted data set, which means that its standard deviation would be the smallest because it is less spread out. And that's exactly what we see here. So choosing a measure of spread or center. So again, if it's basically symmetrical, you want to go with the mean, the average, and a regular standard deviation. But if it's asymmetrical, you want to go with the median and the interquartile range as your measure of spread. Something just Again, important notes to keep in mind. I'd maybe write that down because I don't know if it's going to be on the quiz or not, but might as well have it just to be safe. Okay, using statistics to compare data. So throughout the lesson, you have compiled a set of statistical data for the school activities to present to local businesses for advertising opportunities. So again, we've got all the information we found earlier about concerts, plays, dances, basketball, and football games. We've also listed on here the standard deviation at the very, very end. So now time has come to decide which school activity you would recommend for each company. Let's review the information requested by each company. So the car dealership. Car dealership wants which activity has the least overall change between events. The computer store wants which activity has the highest average attendance at its events. And the clothing store, which activity has the highest typical attendance at its events. So if we look at each of these, the car dealership. So what has the least overall change? Well, according to this one, it's the basketball and football games. And this is determined because of how less spread out the data is. If you look at the chart here, you'll notice that basketball and football games have the smallest standard deviation. Standard deviation is how spread out the data is. So if there's less change, you'll have a smaller standard deviation. And that's the one that has the smallest standard deviation at 75.2, meaning it has the least change, however you want to phrase it. So that's what the car dealership would go for. The computer store. They want the highest average, usually is the mean of the data. So school dances, if we look at the highest mean is the dances. The mean of the dances is 366. So that's the highest average attendance. So the computer store would select the school dances. The clothing store wants the highest typical attendance at its events. The highest typical attendance can be determined by the median. So the median in this case, concerts and plays, wins as well. Because if you look at the median, concerts and plays wins that one, 360, beating the 290, 267.5. So let's make a quick conclusion real quick about what we see here. Let me do a snippet. So the mean is good if you want to find a typical average. Okay, a median is good if you want to find the average of a more asymmetrical set of data. Standard deviation is something to measure how spread out the data is. So a higher standard deviation is more spread. A lower standard deviation is less spread. And you guys know what mean and median are already. They're kind of, like I said, the middle of the data sets.